Oh, got a new person just arrived. The last section, chapter 7's finished after this. We're going to find the difference between two means. Now, I'm not going to rush this, so if I don't end up finishing 7 for it, really doesn't matter because, you know, it'll still be available for another week, so that's good. Well, what we're essentially looking at are two different situations. This one is situation 1, and this is what you do when sigma is known. So if you are told in the question, the population standard deviation for both populations, then this is the formula. And you notice it uses the magic Z-score, and here are 3 of the magic Z-scores. So if you look back at, remember estimates of the mean when sigma was known and estimates of a single mean when it was unknown. Remember those guys? It's going to be kind of deja vu. If I take that guy away and take that guy away, isn't that the formula? Oh, my fingers are too big. Isn't that the formula essentially for calculating one sample's interval, right? For a sample mean. Now, we're looking at the difference between 2 of them, right? So let me make up a story and show you how you could use this. Suppose that there were Scottish rabbits and that there were French rabbits. And we think that these 2 species of rabbits are different in some way. In particular, we think that Scottish rabbits are bigger than French rabbits, right? And you know that, you know, for whatever reason genetically, that can happen, right? And so the way that they test it is we collect a sample of Scottish rabbits, and N1 is how many there were, and we got 120 Scottish rabbits. And we found out what the weights are, and they ended up weighing, on average, 5 pounds. Right? And that doesn't mean every single one of those 120 rabbits weighed 5 pounds, right? Some weighed 4.5 pounds, some weighed 6 pounds, right? And so on and so forth. But they averaged out at 5. And for some reason, we know that the standard deviation of that entire population is 2 pounds. And then we go over and we collect a sample of French rabbits. And let's say there's 200 of those, so we'll call that N2. And basically, you call the first guy 1 and the second guy 2, and you name things that way. And we found that the mean of them was 4.5 pounds. And that the standard deviation was 1.5 pounds. Now, all of this you'll be given in the story, right? You know, there'll be a story about he went out and he captured 120 Scottish rabbits and so on and so forth. And then he went to France and done the same thing and so on and so forth, right? What we're going to do now is create a confidence interval for the difference between them. And the reason we want to do that is we want to see, is there any evidence to prove that Scottish rabbits really are, on average, heavier than French rabbits? Now, you might say, well, it's obvious. Look, that's bigger than that, right? 5 is bigger than 4.5. That is true. But is the difference between them significant enough to guarantee that that wasn't just a fluke of, I found 200 slightly skinny French rabbits and 120 slightly fat Scottish rabbits, right? And so that the information get distorted. So how will we be able to tell and when we're finished? Well, we'll be able to tell because of this property. If all the numbers in the interval are positive, then population 1 is bigger than whatever population 2 is. If all the numbers in the interval are negative numbers, then population 1 will be smaller than population 2. And if the interval is mixed, we can't tell. So we can't tell if one of them is bigger than the other. So we're going to do a 90, 95, 99% confidence interval. And we're going to do it on this story. And if I end up saying that the difference is somewhere between 0.5 of a pound to 0.9 of a pound, you know, something like that, then I can say Scottish rabbits are heavier than French. If I ended up with a negative answer, then that would be that they're lighter. And if I end up with an interval that's got both positive and negative numbers in it, then I'll be able to say we can't tell. So I need a confidence interval. And of course, you'll be told it in the question, but can somebody volunteer a confidence interval that they would like?
95.
Okay, 95 it is. Now, there's a lot of similarities to what you did in 9.1. A 95% confidence interval is the mean of population 1, sample 1 I should say, sample 2, give or take the magic number z-score for 95%, square root sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, let's see what that looks like. £5, take away 4.5 pounds. And for no other reason except cosmetic, I'll switch to red. The magic number for 95% is 1.96 times the square root of 2 squared divided by 120 plus 1.5 squared divided by 200. Are you all comfortable where all these numbers are coming from and where they fit in this formula? If I see a couple of thumbs up, I'm good to go. Thank you, Jennifer. I'm good to go. Now, continuing with this then, that take away that gets me 0.5 plus or minus that horrendous calculation. So let's use a calculator. 1.96 times the square root of 2 squared divided by 120 plus 1.5 squared divided by 200. And the answer I get is 0.413 and a whole load of other digits. Now, if they wanted the answer to say 3 decimal places, then it would 0.414 when I round that off, right? 4138 becomes 414. Very good. Now, just for consistency, what do we call that 0.414? It has a special name, doesn't it?
Margin of error.
It's called the margin of error. Doesn't it also have a letter that they use? Can you remember what letter of the alphabet?
E. Capital E?
That's the one. So if you ever see E equals, do you know they're just saying, tell me what that number is? Now, we are going to calculate. Question?
Yes, so for the margin of error, I've always kind of like wondered how many decimal places that I should actually keep that number.
In it, hopefully the question says to 3 decimal places, to 4 decimal places, that kind of thing. So if it says to 4, then you do it to 4. If it says 3, you do it to 3.
Okay.
Right.
On the Bethany, on the homework or whoever else is having a problem, I do 3 decimal places for the margin of error, but when I continue on with the work, I keep the entire number and do the plus or minus the 0.5 because that's when I was coming, it would be inaccurate for some reason. And that's how I started to get the answers correct by doing the whole big, huge, long number.
So,
okay.
if I can pick it up if I can just paraphrase what she said, I might use that as my margin of error, but when I'm doing the subtraction and adding, I just play safe by using as many digits as I can find. You probably don't need them all, but it's better to be safe than sorry, right?
Yeah, I was just rounding up like that, but then I was so confused on whether it needed to be 1 or 2 decimal places. So yeah, that's probably going to be more helpful is the whole number.
We good? Okay, good question.
Usually do it
Thank
to
you.
Right, now,
5.
we're now going to calculate what I think they call it the lower limit. It's also called the lower bound in some situations. And we're going to calculate the upper limit. And I'm just putting the boxes to be kind of more like what it looks like in the homework. Right, that, take away that, add that. If I add these two guys together, I get 0.914. And if I take one away from the other, I get 0. I better do that. I think it's 0.86, but I'll make sure. 0.5, take away 0.414. And the answer I get is 0.086. I like intervals to be written visually for my benefit. To be written like that. I don't mean a coordinate, it's helpful in my brain to see them side by side like this. Do you see that in this case here, isn't every single one of these numbers positive? So it's saying, look, the difference between the French and the Scottish rabbits is somewhere between 0.086 pounds, but it might be as much as 0.914 pound. Since all of these are positive, can't we say with a 95% confidence that the first guy, the Scots rabbits, are heavier, bigger than the French ones? And very often, that's the kind of thing that we are looking for. Not only do we want to find an interval for what the difference between them is, we're hoping at least to find that that interval is always positive or always negative, because then we can finish off with this little fella. Now, can we pretend in a different world that this first number was negative 0.086? So it would be negative numbers all the way up to positive. In that situation, you couldn't say for sure that rabbits of either country were heavier or lighter than the other rabbits. Because if the difference is positive, it means the first one's heavy. If the difference is a negative number, it means the second number, right? The second population was heavy. And so in that case, either could happen. Are we comfortable with that, the gist of that? Any questions? Can we? I like thumbs up. So I am going to, I won't show you because I've got the answers here and they distract the heck out of me. But we're going to do a question now on from the homework, which is question number 3. At least my version of question number 3. Because, you know, they change the numbers on you. And this is about Old Faithful, Yellowstone National Park. And the first population was data that was collected from 1870 to 1987. And they collected the time interval between Old Faithful, right? That big steam water geyser thing that shot up, you know, you see it in the movies sometimes. How long between one explosion to the next?
I
And
think we
during
already did this problem.
we did?
According to my notes, yes.
We did if you are in the Thursday class. Were you in the Thursday class?
I was not
No.
in the Thursday
We
class.
did it
We
on
did this.
Oh,
You
we
did
have
it on
done this
Wednesday.
one?
Then we
Yeah, I
looked
think
up
we already did
information
that.
on it,
Did
and
you-
that was true.
Ah,
Yeah.
okay.
On when?
Then let's forget about that one. And thank you for telling me. I have 2 stats class. My brain is now, I'm not sure what I've done with one compared to the other. So I can skip by that type of question then, and we can just move on to the second situation then, which I know we haven't done because I haven't done it with anybody. So if situation 1 is, what do you do when sigma is known, which is the rabbit story and Yellowstone geezer story and a few others. I think there's only like 2 or 3 questions, at least right now, that look like that. Let's see if I can find another one, just in case. Right. So I'll just write and note down, at least in the ones I'm looking at. Question 6 is situation 1. No, 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 no. Looks like everything's going to be situation 2. So the vast majority of questions now are situation 2. Okay. So there are only about 2 questions that look like this. So now we're going to do chapter 7.4. Sigma unknown. What I'm calling situation 2. So this is more realistic. You still want to find the difference between 2 population means, but you don't know the standard deviation, right? You don't know sigma 1, you don't know sigma 2. So you would end up with a story that might look something like this. Let's do IQ of football players and IQ of politicians. That way I could get to insult 2 of my favorite groups to insult in one question. Not bad. By the way, the following information is totally made up, right? But just for the purpose of how you would go through the process, right? So there was a big argument about who's got most brains, football players or politicians, right? And so to try and settle the argument, they decided to do a statistical analysis, which is what we're doing right now. And they're going to find the difference between the means. So they found 100 people who play American football, and they found that their IQ was 102. And they also get the sampling standard deviation, and it was 5. Now, you know that if you're given a set of data, can't you get these 2 numbers? You can do them on your calculator, right? You can, we've shown you a way back in week 2 how to do that, right? And a lot of these questions, you'll be able to use SALT to do it for you, right? So if it's a load of numbers, you just go to SALT and you read off mean and standard deviation. And then you went to some politicians and you got hundreds of those, just to be the same. And you found that their average IQ was 98. And that the standard deviation was 4. Oh, I have to change a question, sorry about that. I'm not even sure there are 900 politicians, but I guess you could find 900 if you really had to. Right. It'll come later why I needed to have 2 different numbers here. So what we're going to do is we're going to find what do you want, 90, 95 or 99% confidence interval? Give me one. Pick some at random.
95.
A bit louder, please.
95.
There we go. Now, there should be a formula for it, right? Now, if you look over here, do you see the formula that we used for the difference between two means when sigma is known? I'm about to write down an adjusted, altered version of this formula for the new situation. It's going to be x1 bar take out x2 bar. That shouldn't be a surprise. I am not going to do a magic z-score, but I am going to do a different letter of the alphabet score. Who is he?
T.
So I'm going to do a magic t-score for 0.95, followed by a square root. Now, I don't know sigma 1 and I don't know sigma 2, but don't I have replacements for them? You see, I can use S1, the standard deviation of the sample of 1 and of 2. And so the formula becomes S1 squared over N1 plus S2 squared over 10 N2. Does that formula look close enough to this one that it kind of makes sense what it is? You know, why it is the way it is. Now, when it was a Z-score, wasn't it simple because it was the same Z-score every time? You know, if I want a magic 99, I use that Z-score. A 95, I use this one, right? But doesn't this guy change? And didn't it change because of a thing called degrees of freedom? Now, when it was a single sample and you had 50 numbers, wasn't the degree of freedom 49? You took one off it. And then you had to look at a big table and read off what the magic number was, right? We're going to have to do it again. But it's harder now. There are two samples, one with 100, one with 900. Now, you might think you add them together and take away one. Actually, in some textbooks, they take away two, but that's fine. But not in this one. And where am I going to put it? I'm going to put it up here. To get the magic t-score for 0.95, you use the smaller number and you subtract 1. So in this case, won't I use 99? Right? 900 or 100? And the reason I'm assuming that the textbook is erring on the side of safety. They're saying, what's the worst case scenario? Well, pretend you've only got 100 data points, because in one case, that is all you have. And the degree of freedom is always one less than that. So that's what we do. So in this case here, won't the degree of freedom be 99? Which means that we should go hunting for that magic number. I have got a PDF floating around, and I'm going to go and eventually, when I get round to it, I'm going to put this PDF on Canvas so that you can just print it out or have it on your screen when you do these questions, because it's a real pain in the butt, isn't it, to go in and out all the time to try and find it, and then you lose track of where you were. But right now, you're just going to have to wait until I get round to doing that. Hold on a few more seconds. Here we go. Are you looking, I hope, at that table that I was talking about? Can you see it on the screen in front of you? Now, degrees of freedom in this story were 99. You know what happens is you don't quite get all the numbers you want. So would you agree, although I don't have a 99, can't I use 100 because it's darn close to it? Now, sometimes you're going to have a number. Can you imagine the degrees of freedom were 22? So won't I use this row here, right? Great. Now, I wanted 95. So 95 is here. So I'm coming down here. 95 coming down here. And 1.984. Let's do that in red. 1.984. Do you know, to me, that's going to be the hardest bit of this, just finding who that blinking magic t-score is. Because aren't the other numbers in front of you? And then it's a calculator job. So let's move on and upwards. It's going to be 102, take away 98. Plus or minus 1.984. Square root of 5 squared divided by 100 plus 4 squared divided by 900. That ends up being 4 plus or minus whatever the I'm going to have to leave the screen now because I've got what I needed. So 102 take away 98, that's this bit. Give or take, magic t-score, that guy 5 squared over 100 plus that guy 4 squared over 100. Take me to the calculator, and 1.984 times the square root of 5 squared divided by 100 plus 4 squared divided by 900. And I get plus or minus 1.027. Can we pretend it was a 3 decimal place question? And there's my margin of error. The difference between IQs is about 4. Doesn't that mean football players are more intelligent IQ-wise? And what's the margin of error? Well, it could be give or take 1, roughly. So if we go into the upper limit, and I guess I should do the lower limit first, so I'll squeeze that in. The lower limit is 2.973, and the upper limit is 5.027. And then there's very often a little question where there's 4 choices, and one of those choices will be, there's enough evidence to show that football players have a higher IQ than politicians. Agree? How do I know that? Because aren't these guys all positives? So the difference is positive, means the first thing is bigger than the second. So the IQ of football players, the first thing, is bigger than the IQ of the second guys. And I know, pretend it was that one, right? And you pick it. I'm seeing some nods. It's not that big a transition, is it? From a knowing who the sigma is to figuring out what it is when you don't know it, right? The formulas are not horrendously different. It's this awkward piece here, isn't it? Getting the t-score. Once you've identified him correctly, most of the work's done by your calculator. I think we need a joke then. Right. So I'm picking on politicians. You ready? What is the difference between a politician and a snake?
Nothing.
Say it again, please, Erica.
I said nothing.
Ah, that's your version. No, some people like snakes. Almost your answer, right? How do you tell if a politician is lying?
If his mouth is moving.
Yep, that's an old one. Did I tell you the joke about the guy who goes to the doctor? And the doctor's looking kind of worried and he says, tell me, doctor, what's up? And the doctor says, I have good news for you, and I have some bad news. And the guy says, okay, tell me the good news. He says, you'll be dead in 6 months. And he goes, that was the good news? I said, yeah. I said, what was the bad news? Well, he says, I should have told you 6 months ago. But wait, there's more to this joke. You're in luck. You need a brain transplant. That'll save your life. And the guy says, I've never heard of one of them. Says it's cutting edge, just coming on the market. Bit expensive, but it'll save your life. And the guy says, well, how expensive is it? And the doctor says, well, it depends on what kind of brain we use. So he takes him into this next room, and there's 3 big jars of brains. And he goes to the first jar and says, in this jar, we have English professor brains. English professor brains. $5 an ounce. And the guy kind of saw him and says, well, that's pretty cheap. So he moves to the next one and says, what about this? He says, oh, a little bit better, this one's. These are mathematician professor brains. These will cost you $10 an ounce. The guy just says, okay, I could maybe afford that. And then he goes to the third jar and he says, what about these ones? He says, oh, these are politician brains. These are going to cost you $1,000 an ounce. And the guy looks at the doctor and says, no, I don't understand that. I mean, why? How could it cost that much for a politician brain? And he looks at him and says, have you any idea how many politicians you have to kill to get an ounce of brain? Okay, I got at least 2 thumbs up. I got it. Oh, you've got one. Go for it. As long as it's suitable, go for it.
I think it is.
Oh, the thinking could be awkward. Okay, go for it, Holly. I'll trust you.
My mom posted it the other day and I thought it was funny. Okay, so after 35 years of
sorry, Holly, before you continue, if I think it's going to be unsuitable, I'll just say, whoa, right? Just in case. Go for it.
Okay. No, it's not that bad.
Okay.
Some people are just sensitive. I don't know. After 35 years of marriage, a husband and a wife went to see a marriage counselor. When asked what the problem was, the wife described the problems they had since they've been married, which was like neglect, lack of intimacy, loneliness, etc. After a pause, the counselor got up, walked around the desk, and after asking the wife to please stand, the counselor embraced and kissed her lovingly as her husband watched. And then the wife quietly sat down in a daze, and the counselor turned to the husband and said, "This is what your wife needs at least 3 times a week. Can you do this?" And he said, "Well, I can drop her off here on Mondays and Wednesdays, but on Fridays I go fishing."
Oh, God. Oh,
That was a good
bad.
one.
Oh, God.
All right, I got one.
Oh, this is getting worse.
All right,
The usual rule has to be suitable, but go for it.
all right. What kind of dogs can jump higher than buildings?
I don't know. What kind of dogs can jump higher than buildings?
All of them. Buildings can't jump.
Okay. I'm putting an end to these jokes by telling you the worst one I know, and that'll probably shut us up, and we can continue with this after that. So you ready for this? I'm warning you right now, this is really horrible, but I like it because it's that bad. This little old lady goes to the vet and gets taken into, the office and the big table there, and she has a little crate for keeping her pet and her dog, and she brings it out and she puts them on the table, and it's as stiff as a board. And the vet looks at him and says, "I can't do anything for your dog, it's dead." And she says, "No, are you sure it's dead? He sleeps a lot, maybe he's just sleeping." And he goes over and he looks at the dog and it's not moving. And he says, "No, it's dead." And she says, "Well, can you at least do some tests?" He says, "Okay." I've got a couple of tests. And he goes into the back room and he comes in with a Labrador, big Labrador dog. And the Labrador dog goes round her dog and it sniffs at it and it growls, it pushes it with its nose, and obviously nothing happened, and he takes the lab away. He says, look, your dog's dead. He says, no, he's like that with other dogs. He doesn't move much. He says, well, I've only got one more test. And he says, I'll go and get it. And he brings in this cat and it's in a box. It's a vicious looking animal. And he opens up the cage, you know, the door, and the thing comes out and it jumps right on our dog and it goes in the top and it starts doing its claws and hisses and scratches it and finally grabs it and it's scratching and biting and sticks it back in and closes the door. He says, have I convinced you your dog's dead? And she said, yeah, must be dead after that, you know. And so she says at the end, well, how much is it going to cost us? And he says, it'll cost you $1,020. She's kind of puzzled and said, how come? He says, well, it was $20 for the consultation, and it was $1,000 for the lab work and the CAT scan. Let it sink in, Holly. Okay. I did warn you, it was bad. Okay, then continuing then with this process, the good news is that really the next, I think I should be able to do 2, if not 3 questions. They are pretty much going to be another one of these, right? They'll just change the story on you, but most of the process is going to stay pretty much the same. There are a couple of questions about does this get bigger and does that get bigger, but that in itself is not too big an issue. Okay, so my next example is going to be question 8. Now, in question 8, you'll be able to use salt in a minute, but I just want to get a bit out of the way first. There are 2 samples in question 8. One of them is called, I think they call it region 1. And the other one's going to be called region 2. And region 1 has 12 numbers in the sample, and region 2 is 16. So we are going to generate, eventually, a confidence interval. Good grief. A 98% confidence interval. That's one I've never seen before. A 98% confidence interval based on this information and some other stuff that's going to come later. All I'm going to do right now is figure out the magic t-score. I've actually never seen a 98. It'll be interesting to see what number it is. How many degrees of freedom?
11.
Right. Smallest number, take away 1. Now, I hope that that table I've got has got a 98 column in it, or else we're kind of up a creek without a paddle. So let me find that guy and go in and see if we've got a 98. Oh, would you believe it? There's a 98. Do you see it there? Am I showing the T table? Can you see what I'm saying? 98. Now, degrees of freedom were 11. So when you put them together, the magic T-score is 2.718. Are you all comfortable about how, from the story, the very brief story I gave you, how we got the magic T-score? That's always going to be, in my opinion, the hardest thing to do, right? Is to get that guy. Now I'm going to leave this and we're going to go to the question itself. And we'll talk a little bit about the story. Sometimes they go into a whole load of stuff that really is a distraction. But anyway, here goes. Inorganic phosphorus is a naturally occurring element in all plants and animals, with concentrations increasingly progressively up the food chain. So fruit has a little, veg have more, cereal has more, nuts have even more phosphorus, and dead bodies have the most. Okay. Geochemical surveys take soil samples to determine the phosphorus content. A high phosphorus content may or may not indicate an ancient burial site, or at least a food storage site, or even a garbage dump. So you can imagine one of the tests an archaeologist might do, a kind of first test, is just take soil samples. And if he gets a really high phosphorus level, he's thinking, there's probably something interesting under here. It could be just dead bodies, right? Burial site. Or a food dump. You know, in the olden days when, we're talking really olden days, people didn't have refrigerators, believe it or not. So ancient man very often dug holes and put the food in it and then covered them up with soil. And the reason they did that is, I don't know how far down you need to go, but let's say it's 6 feet. Do you know if you go 6 feet down, doesn't the temperature keep pretty stable, no matter what the weather above is like? And so that was their refrigerator, if you like, in those days. So here is some data, and we're going to look at two groups. In region 1, these are the phosphorus levels. In region 2, this is the phosphorus levels. And we are going to get all of these numbers. So sample 1, we're going to get its mean and standard deviation. Sample 2, this stuff here, we're going to get it. But we should be able to do it using salt, fingers crossed. So right now, if I click on this, do you see that I've got region 1 highlighted? Can you see what I'm saying? Okay. And now if I go to the top and I go to descriptive statistics, the mean is 747.5, and the standard deviation is right next to it, is 170.4073. Do you see where I got those numbers from? Right, I hit the salt button, and then I said to it, I'll go, I think I can go back on this, right? Now, if I wanted region 2, wouldn't I uncheck that one and recheck this one? And that way I could get the second one. Now, if you do that, you are all shooting space. This thing, there we are. Don't you disappear on me. Here we go. Do you see the numbers that I was? Oh, shooting space. These are the numbers that I got from that thing. Now, what we're going to do is an 85%. No, you're not. Do you know Web is saying, if, from my perspective, see if I leave a question and go back, it randomizes the numbers. That's why when Holly does question 8 and Denise does question 8, you don't have the same numbers, right? If you ever check with someone, they'll say, that's not the numbers I'm looking at, right? So can we pretend that it was 98 that I had a minute ago, because I don't want to have to recalculate my T and then lose it again. So in that case then, all I'm writing down right now is what the mean and standard deviation of the first sample is, and what the mean and the standard deviation of the second sample is. And 78 point, I'll call that 9, and 212.1463. Okay. So basically, what you do is you use salt to get all the data that you need. And it's all here. The mean, oh, darn it, in space. Everybody here should be amazed at how I don't swear. Have you noticed I've not sweared once yet? Okay, no comments. Magic T-score, those two guys. Let's get a 98% confidence interval for the difference. The formula is x1 bar, take away x2 bar, plus or minus the magic T-score, followed by that fella added to that fella, right? So x1 is 747.5, take away 738.9, plus or minus 2.718 times this guy. No, it's not this guy. This guy's a number. 100. Tell you what, can I cheat and just pretend it's 170 and you can pretend I did it over 12. And the other one, I'm just going to pretend it's 212 squared over 16, right? Because I'm really just focusing on the process here and I don't want to get too caught up with 4 decimal places all over the place. So if you take the first guy and subtract the second guy, 745.5, take away 738.9, you get the answer 6.6, give or take 2.718 times the square root of 170 squared divided by 12, add 212 squared divided by 16. And the answer is E. Let me check that again. No, it's right. Why do you think I was hesitant? I checked the numbers and they're right.
Because it's so big.
Yeah. What that tells me is that the variation in phosphorus levels is all over the place. And if you take this number, doesn't it swamp that number? So if you do the interval, on one side, aren't you going to get a really weird negative number? On the other side, probably just as bad, but a positive number. So that's 202.3 on this side. And on the other side, it's 6.6, take away 196.3. On this side, it's negative 189.7. So what I can tell you for sure is that there's no obvious difference. Between the two regions. If everything was positive, wouldn't that mean region 1 had a lot more phosphorus in it than region 2? And if they were all negative, region 1 would have a lot less phosphorus than region 2. But a bit of each is a forget it. Which to me kind of matches. The numbers they've got are different because they changed the confidence interval, but the numbers they've got in front of me are negative 103 and positive 120. So it's kind of the same story, but with different numbers. Can you hear my dog back there? Can you? Do you want to see her? Okay. Watch this. She hates being picked up. There she is. She is absolutely terrified. She's like frozen with fright. She won't even lick me. That's how scared she is. Oh, it's gone. Is it okay to put you down now?
She hates that.
Come on, kiss. Nothing. Very good. See the other one? You've seen Bailey. If I picked him up, head out, he'd stay there all day if I let him. Okay, that's pretty much the end of that question. Let me make up one to finish with then. No, maybe two. So I'll do one of theirs with salt, and then I'll do one of my own. Okay. Let's pick something different than phosphorus. It's kind of boring. Okay. I don't know how relevant this one is, but this is question 10. They have two companies. No, not two companies, two industries. Population one is tech companies. And they did a sample and they asked them, what percentage of your revenue was from selling to other countries, right? Foreign revenue. And in this first one, there was 16 numbers in that. And although you'll see the data in a little while, but it looks like it ranges somewhere in the region of 41 to about 60, right? And then in the second category, it was basic consumer stuff. I think basic consumer stuff is like, you know, washing up liquid and stuff like that, I guess. In this, there was almost the same number. The sample size was 17. And they had a whole load of data on this lot and a whole load of data on that. And I'm just going to go into salt and do it. And oh, let's set it up first. So I'm going to find the mean and standard deviation here and here. I'm going to find the mean and standard deviation here and here. And we are also going to, in this question, we're going to get a much more normal 90% confidence interval question, right? So what's the only thing that I'm missing that I need to maybe calculate before I start doing salt?
The T number.
Yeah. In this case, what's the degree of freedom going to be?
15.
Great. Smallest one, take away one. Now, that means I have to go to a different piece of paper. But hopefully it won't take us too long to find it. Here we go. Now, if you want a 90%, it's this column here. I just noticed something. I've got a mouse pointer that's a little hand. Do you see that mouse pointer? Oh, good. So when I was moving this up and down, I thought you might be seeing it, but I wasn't sure. So do you see me moving that little mouse pointer that looks like a hand? That's actually quite helpful. So I want a 90%, so that's why I'm in this column. And I want degrees of 15, so won't that be the 1.753 guy? Can you see where I got that guy? 90%, right? 15 degrees of freedom, 1.753. Now I'm going to go to the homework. We're going to look at what that data looks like, and we're going to use salt. So here it goes. Click on that. Move over here. Right. So are you looking at question 10 now, I hope? Right, you can see the answers here, but let's verify what they are. So I'll hit the use salt button, and I'll get the technology first, and I'll go to descriptive, and I'm changing the question to make my life easier. The mean is now 51.6, actually 51.7 if you round it up, and the standard deviation is 7.9. So there's the mean here, and there's the standard deviation, right? And then if I go back one and I do basic consumers, I should be able to get theirs. And the mean in this case is 33.6, and that the standard deviation is about 12.3. So just to make my life a little bit easier, I'm rounding off to a lot less than you meant to for the question. Well, hopefully that's not a big deal, right? Can you imagine doing it to 4 decimal places? Okay, so here goes. X1, take away X2, magic t-score, S1 squared over N1, S2 squared over N2. This guy is 51.7, take away 33.6, give or take 1.753, square root of that guy squared divided by 16 plus this guy squared divided by 17. Right, on my calculator then, 51.7 subtract 33.6, we get 18.1. And then 1.753, then that square root guy, then this guy, six point 6.3. You happy with the margin of error, where it came from? Okay, if we do a quick subtract and add thingy, you get 11.8 on one side, and you get another 24.4 on the other. Actually, these are percentages, but that's fine. So what does that tell me? Since that difference is all positive numbers, doesn't that mean that there's strong evidence, 90% evidence, that tech companies sell a larger percentage overseas of their revenue than basic consumer products are? And that difference is at least 11% and could be as high as 24%. Because this isn't every tech company in America, and this isn't every basic consumer, aren't these samples of each kind of company? But we've now got quite convincing evidence that there is a definite difference, which is why we do this. Prove that there's a definite difference. Are we good? Right, so I have no idea how this last question is going to go. If I'm really lucky, we will get some conclusive evidence. But then again, maybe it won't. So I'm going to have to leave this for a second, because you lot are going to supply the data. And so how are we going to split these? Well, the easiest split is male against female. It's easily split to do. And I am going to ask you, what can I ask you? I need to ask you a question where the answer is a number like nothing, 1, 2, 3, 4, right? I don't want numbers that are too big because I'll be typing them in forever. So what could I ask? Okay, I will be totally sexist because I'm allowed to be, and you will prove me wrong, which you're allowed to do as well. And I'm going to ask you how many times you went shopping in the last week. So it might be I didn't go to the shops at all, or I went 5 times. So, and I'm going to make a very bad assumption that the females went to the shops more often than the males, and you'll prove me wrong probably, right? So let's do the guys. Those who want to take part, will you tell me? I've been twice, so.
I've been twice as well.
I think I've been once.
I've been once.
Right. Anybody else?
I've been once.
Right, we're doing the guys right now. Morgan, you're next. Any other guys that want to volunteer? That might be all the guys in this
I've
class.
been 0 times.
You've been how many again?
0.
Okay,
And 1 for me.
and 1 for you.
0.
And another 0. Okay, that sounds pretty good. So 2, 4, 6, 8. So that's a sample size of 8. Okay. You want to volunteer, you just shout out the number and I'll start writing them down.
I've been once.
0.
3.
1.
0.
2.
1.
What was that number?
2.
2, right. Anybody else? There might be some people in the chat. Let me go in case they've gave their contribution. I got another one in the chat. They said 1. Okay. Anybody else before we continue this? Have we got any other volunteers? I really could do with an outlier here. A shopaholic who wants to admit to their shopaholicness. Nah. Okay. 2, 4, 6, 8, 9. So that's a sample set of 9. So we're going to have to get a 90% confidence interval. The degrees of freedom are going to be 7. And that the magic t-score is going to be that guy, right? So I'm just going to have to close and open all that carry on again. So a 90% is right in the middle here. And I want to go down to 7 degrees of freedom. So 1.895. So far, so good. Now I'm going to close that off. I'll go back in for a few seconds, only just to show you where I am. Here's the data, 2 samples, magic t-score. I am, of course, missing quite a lot. Great. Now, if this was the data in the software, wouldn't we hit the salt button and it would do it? But in real life, you don't always have salt buttons, right? So I'm going to show you the kind of the good old-fashioned way of doing that, and that's by using a calculator. So I'm going to show you, I think it's this one. Right, you should be looking at a big version of a TI-84 right now. Is that what you see? Okay. So you just, I'll do the males first. Does anybody, it's a while since we've done this, does anybody remember how you get data into your calculator so you can find means and standard deviations and all that fun stuff? What button do I press first? Anybody remember?
Yeah.
Yep. And choice number 1 is edit. And the data for the guys was 2, 2, 1, 1, another 1, a 0, a 1, and a 0. And over here, I might as well put in an L2 what the females are. So they were 1, 0, 3, 1, 0, 2, 1, 2, and 1. Okay. And different sample sizes are fine. Now I hit start button again. Where do I go to find means and standard deviations?
You go over to calc.
And choice number 1. Now in my calculator, it's the old one. I have to tell it that my data is in L1. For some of you, you have a little menu system that does the same job. So to get L1, you hit blue button, 1. And now it's ready. And oh, would you believe it? The mean was a perfect 1. That was just sheer luck. And the standard deviation is SX. And what's that, 0.755 and a whole lot of other stuff? Can I just call that 0.8 because we don't really want to get caught up too much in the details. Now I would like to go back and I'll go over to calc and I'll do one variable stats a second time. But now I'm going to do L2 because that's where the females are. And they are 1.2. And I'm going to round that standard deviation off to 1. And now I can go back to where we were. And basically, don't we have everything that we need? I know it's all kind of in various places, but isn't everything we need in here somewhere? Do you think that that difference is big enough to prove that women, females, go shopping more than males? Do you think 1.2 compared to 1 is a big enough difference that it would show up? In other words, you got a whole load of numbers that are all positive or all negative in your interval. Okay, we've got one nodding head. My answer is, I don't know. It's hard to judge, right? So you may be right. So to get a 90% confidence interval, it's going to be x1 bar, take away x2 bar, the magic t-score, all of this guy. One take away 1.2 plus or minus 1.895, the square root of 0.8 squared over 8 people plus 1 squared over 9 people. These two, you get a negative number, which is okay. Negative numbers happen. So I'm going to go 1.895 times the square root of 0.8 squared divided by 8 plus 1 squared divided by 9. And I get the answer 0.8. Now, if you take this number away, it's -1. And if you add it, it's positive 0.6. So what this tells me is that there isn't really any significant difference, right? There's no evidence here to show that women, I mean, wouldn't it just take one guy who liked to go 5 times or one of these 3 to be a 0, and you could actually have switched places? I mean, that's how close the data was. And so based on a very small sample, I agree, but taking that into account, there's still no evidence. So when you're going through any kind of statistical analysis, that's what we call this process, you will come across answers where you spent, I don't know, 5 days collecting the data and putting it into tables and doing a whole load of clever stuff. And at the end of those 5 days, oh, well, I think maybe you should just say to yourself, no significant difference is an answer. Doesn't it mean that they're just about the same? There's no reason why one group should always be bigger or better or less than the other group. Can't there be lots of situations where both groups are pretty much the same as each other? And that's to me, that's important to know as well. So it's not totally wasted just because that happens. Unfortunately, some people who want a particular answer to be true would do something like this. Suppose I was a horrible sexist and I was going to write a book about males and females in shopping. I have no idea why I'd want to, but suppose I did. And I wanted to kind of pseudo back it up with pseudoscience. Couldn't I do 10 different samples like this? Right? And one of them probably would be the guy I was looking for. You know, if you do something often enough, don't you just get a positive answer, right? And what do I then do? Because this is totally cheating. Don't I only publish in my book the results from that one sample? And if no one ever knew, which they probably won't, because I won't tell them, right, that the other 9 didn't do that. The other 9 looked like this. Can you see how sneaky that is? Which is why in the scientific world, they have a thing called peer review. Have you ever heard it? Essentially, if someone comes up, even in social sciences, which is the worst science in the world, in my opinion, there is a lot of garbage out in the social science world. But even in the social science world with peer review, if someone comes up with this, what you should do is someone totally unconnected that has no dog in the fight does it themselves. They go and get a sample of guys and women, and they find out how many times they went shopping. And they will pretty soon figure out, well, I done it and I never saw what you saw. And then somebody else does it and said, yeah, I did it and I never got it. And so what would happen then is that pseudoscience result would get discredited. Because if it was true, shouldn't it be repeatable? You know, if you did it 10 times, 9 out of the 10, it would say, this is what happened. And the other one was the odd one out, right? The one that kind of had both sides. So that's kind of the theory behind the process. And we are kind of, I think, a natural finish. Is there anything that you have issues with 7.4 before I leave? If there is, I'll try and go over it. I'm going to spend the last 10 minutes doing that question that I promised to, I think it was Josh at the start. So I'm going to go over one of the, I think it was 7.3 if I remember, and I'll do the, you know, the whole working thing. So if you're cool with 7.3, you can leave. Oh, did you say hi? Say hi first.
I had a question with 7.4.
Okay, we'll do 7.4 first because that makes sense to get that out of the way. What's your question, Brittany?
So like in question 8.
Okay, let me have a look at question 8. Oh, shit. Hold on, my computer's being weird. Oh, I got it. I think I got it.
Okay.
Right, question 8.
So it has like 2 different regions to use.
It says, for this problem, carry at least 4 digits after the decimal in your calculation. That's not what your problem is. You said there's 2 somethings. I'm trying to see what that is. Maybe I'll share the screen and you can tell me from what I'm looking at what your issue is.
Oh, okay, I can share.
Okay, so right, this is question 8 from 7.4. Oh, this is my question 8. Does that look similar to your question 8?
No. Is that 7.3?
This should be 7.4. I have no idea if this is 7.4 because let me go back in out and then 4. 4. Right. I could have hit the wrong one, you're right. We're looking at 7.4 question 8. Agreed?
Yes. Yes.
Okay. So.
Yeah, it's just like that one.
Oh, Well, I can go to 8 because I've got the answers in front of us, so that might help.
Okay.
So there are two different groups, this group and that group,
Mhm.
right?
Yeah.
And we go into solve and you get these two numbers from group 1 and you get this mean and standard deviation from group 2. Is that not working?
I got that part.
Okay.
The next part.
Lower
So-
limit and upper limit.
Is this the one that you have to use the T and then you have to use the chart to find it?
Exactly, yes.
Okay, that's the part that I'm having an issue with is because
Right.
it has 2.
Well, it has two numbers here. Is that the 2 that you're meaning?
Well, see, like how like the information's like spread out. I'm confused on how to find T when there's 2 ends, and then
Okay, here we go. There's a rule for that. There's two different samples. One is 16 and the other's 12, right?
Yeah.
Pick the smaller sample size and subtract 1 from it, and that's 11. So the number that you get from that table is degrees of freedom 11. So there's only one magic t-score. This calculation uses numbers from x1, x2, s1, s2. It uses all the numbers in one place, but there's only one t-value, and you get the t-value by picking the smallest sample size, in this case is 11, and in this case you want, what, an 85% confidence level, well, at least in my question. So what I would do is I'd say, okay, 11 numbers. So I go over here. Oh, that's weird.
I think that was it. That's all I had was just which end to use.
Okay, so you're happy with looking up 11 because my table has went weird.
Yeah.
I don't know if
I'll-
you can see, I can't see it now. It's just full of colored things.
Yeah.
If that's all you've got, we are good. If not, tell me and we'll continue.
Okay, I think I'm good.
Okay,
Thank you.
right. You are welcome. I'm going to try and close some of these windows off because I think that's one of the problems. So where are you? Who was it that asked again?
I have a question.
Oh, yes, Hannah.
So the formula where it's like where did I wrote it down? It's like the formula, where's my notes? Okay, it's like the x1 minus, like the whole formula from the beginning.
Yeah.
I can't get it to work. Every time I do it, I always get it wrong. Like no matter how I enter it on my calculator, like I enter it the way I like the way it looks, and then I enter it the way you do it, but every single time I always get the answer wrong. So I'm just
I wish I was with you and I could see the button pressing because it could be something really simple. But I can't kind of see it. So I'll try it again.
I don't know. I just
when I-
don't understand. Like
What
it's
kind
just
of-
out over here.
Sorry, what kind of calculator are you using?
I have the Texas Instrument one. It's the 36X Pro.
Oh God, that's a different calculator.
Yeah, I have
That's a
different
problem.
calculator. Yeah.
Right. Well, I suggest what you do is there's a program that I have. I think I gave a link to. If not, I'll send another link to you. And what it does is it gives you an emulator of the TI-84. So I'm going to show you what that looks like. It's this guy here. Do you see it?
Yeah. Mine
So if you can get a hold of that, you'll have the TI-84. Because if you're using a different calculator, I'm not at all sure that the buttons I told you to press will be the same effect as they are in a TI-84. I don't even know that particular calculator you're talking about that well. Does it look very like an 83? Does an 83 look like the 84?
It's like this.
Yeah, it kind of looks the same.
Yeah.
So, does it have? Or well, are you talking just about the calculation part, right? Hitting
Yeah,
all the
I
right
just
numbers.
can't do the math. Like I like enter it in so many different possible ways.
Okay, what we're going to do here is, I'm going to type on my calculator a set of things, and you're going to type in yours, and then you're going to tell me what the answer is, and we'll see if we get the same answer. And if we get a different answer, I might be able to figure out what you're not doing. Okay.
Okay.
So don't worry about where the numbers are coming from. Just look at the screen and kind of type the same numbers, right? So let's suppose the number was 0.5 first, right?
Mhm.
Then times, then you do a square root. Does it look like that?
It doesn't put a parenthesis. I can just type it fully into the.
Right, put a parenthesis in. Let's start
Okay.
with that.
Okay,
In
I
case
can put it
that's,
there.
in case that might be the issue, right? Could be
Mhm.
as simple as that. Now, after that, you have a number. Let's say it's 0.7 squared divided by 10.
Okay.
And then you'll add, let's suppose the other one is 0.5 divided by 20, just for argument's sake. And then you close the brackets. So you're going to go 0. You've got your bracket, 0.7 square button divided by 10, add a 0.5 divided by 20, close the brackets.
Mhm.
And now I'm going to hit enter. And you're looking at that number.
Mine actually put the 0 in front of it.
That's fine, but is it 0.136?
0.136014705.
I think we've cured it. You need a bracket.
Okay, because I put the brackets too. Like here, let me try it without the brackets, because it should usually it's just the same.
Okay.
Oops,
I
not what
can't
meant
do
to
it because my calculator puts the bracket in automatically, so I can't stop
Yeah.
it from doing it.
You can also find all of the answers on SALT. You don't even need your calculator.
Well, I guess you could go into SALT and just type them in, right? Is that what you're thinking?
Yeah, I got the same exact answer. I don't need the brackets.
Well, we just did one and it didn't work. Can you find a question that you physically did that didn't work then? And maybe I could try that.
It was all of them, to be honest. For the 7.4. Like to the point where I'm running out of tries.
I'm
Hannah, could
at a
I show
loss.
you maybe how to do it on SALT?
Yeah, I'll tell you what I'm doing. I'm going to share screen,
Yeah.
right? And you're going to watch. I've forgotten who it was now. Who is it? Bethany?
Okay,
It's
I
Jennifer.
kind of understand a little
We're
bit.
going to share screen. Okay, I've now put it on all participants. So whoever wants to share, share the screen and show me what you're doing.
Okay, let me see.
So it's Jennifer. Okay. Okay.
Like 6 is
Okay.
the most recent.
Here we
problem.
go.
Like
Okay, can you see what I'm doing?
Yeah.
Yeah.
Hannah?
Mhm.
You're on 7.4, right?
Yep.
Okay. So I'm just going to show you how I would do this one. You go in and you just push SALT.
Mhm.
And it downloads everything. And then you go to descriptive statistics. And here are your answers for the first part of the problem.
Yeah, like I can get that far.
So you can get this part.
Mhm.
Okay, can you do this part?
That's the part I'm always getting wrong.
So you can do this in SALT.
Okay.
Okay, so let me show you how to do it.
Okay.
It's time consuming, but you always get the right answer. Okay, so you go over here and you change this to 2 sample T, and then you start putting your numbers in. You take the mean for this one. Uh, 36.
You are very fast.
Mm.
You must have been doing this a lot.
I've been doing this a lot. There's a lot of problems like this.
Correct.
38. And then let's see, our question wanted a 99% confidence interval. So you go confidence interval and you change it to 99%. And then you put generate results. And this will give you your upper and your lower limit right there.
Oh, okay.
Dang,
Thank
that's
you.
intense. That's awesome.
Yeah, thank
is.
you.
Genius.
Everybody is so welcome.
How did you figure that out?
Yeah.
Bro, that makes everything so much better.
Thank
You guys are
for
so
sharing
welcome.
that.
Yeah,
It was a lot of trial
I'm
and
going to let
error.
you. Yeah, I'm going to let you teach next week, and I can have a break. That was very good. Thank you very.